Okay, hello, welcome back. In the previous video, we saw how we can define work of a force over long distances that are not infinitesimal. And we saw we can write it in this integral form. And as long as we know, we can somehow calculate force times cosine of the angle between the force and displacement. We should, in principle, be able to take this integral. There are many examples that this integral is easy to take. And the first one that we are going to look at is work of the force of gravity or work of the force of weight. Consider, again, as always, a particle randomly moving, and you have this force of gravity, W equals mass times acceleration, gravitational acceleration g. And as we go from one point, S1 to S2, we want to calculate the amount of work done by this this force of gravity. And here is another one of the cases that you need to be kind of clever on how you formulate your problem that may help you with the solution. To write these vector equations, I need to represent these vectors by numbers. And one thing that works particularly well when you're dealing with gravity is rectangular frame, because the force is always along just one of the axes. So let's create the XYZ rectangular frame. Now what I can do is write the force vector as minus mg in the k direction. And if I have a small displacement, call it dr, I can write dr as some displacement along x in the I direction plus some displacement along y in the j direction plus some displacement along z in the k direction. And now, well, actually, I should have wrote it this way for this particular problem. It is f dot dr. This is better. And now I have both of these expressed in rectangular coordinates. So I can write work from 1 to 2 equals integral of f, which is minus mg k dot product with dxi plus dyj plus dzk. And see what happens. When I take this dot product, I have minus mg dx I dot k minus mg dy j dot k. Let's put this in parentheses. Minus mg dz k dot k. And because I and k are perpendicular, so these are perpendicular to each other, the dot product is 0. Similarly, j and k are perpendicular, so the dot product is 0. And the last one, k dot k, is going to be 1, the length of the vector, times 1 times cosine of cosine of 0 degrees between them. which equals 1. So k dot k is always 1, or any of these I dot I, j dot j, and k dot k. These are all, they all equal 1. So what I end up with, I write it here, that u from 1 to 2, the only term that remains is minus m times g times dz. And now note that my integral variable is only along z. So all I need to do is figure out how much I have displaced along the z-axis. It's going to minus mg z2 minus z1, or minus mg delta z. And that is the amount of work of force of gravity, or simply work of gravity. It is related to the weight and only the amount of displacement in the vertical direction. Note that it is negative because the force of gravity is downward. If you increase your elevation, you have a higher height, the work is actually going in its opposite direction. That's why we have this negative sign. And yeah, that is the work of gravity. You can see how fairly easily you can calculate the amount of work. You don't have to worry about taking the integral, as long as you know how much you have displaced in the vertical direction. Just go ahead and use negative mass times gravity times change in height to get the work of gravity. So I think that is all I have here. We'll look at other examples in the other videos. So I'll see you then.